Hey there! Welcome back to our video lecture series on continuity and continuous functions. In this module 9, we're diving deep into a fundamental theorem in calculus known as the intermediate value theorem (IVT) for continuous functions. So, what is the big deal with the intermediate value theorem? Well, imagine you're driving from one point to another, and you're tracking your distance traveled along the way. The intermediate value theorem tells us that if your journey is smooth and continuous, you're guaranteed to pass every mile marker between your starting point and your destination. Theorem 11. The intermediate value theorem for continuous functions. If f is a continuous function on a closed interval from a to b, and if y0 is any value between f of a and f of b, then y0 equals f of c for some t in the closed interval from a to b. The intermediate value theorem tells us that if we have a function f that is continuous over a range of values from a to b, and we pick any number between f of a and f of b, let us call this number I0, then there is guaranteed to be some point, which we'll call c, within our starting range from a to b, where the function will take the value I0. So if f is a continuous function on a closed interval from a to b, and I0 is any value between f of a and f of b, then I0 equals f of c for some c in the interval from a to b. Let us delve into the proof of the intermediate value theorem. The proof relies on the notion of continuity, where the function's values remain close to each other as the input values get closer. We'll first establish that the function f of x achieves its maximum and minimum values on the closed interval from a to b. Then we'll show that any value between the minimum and maximum can also be attained by the function, thus proving the intermediate value theorem. Now, let us explore some applications of the intermediate value theorem. This theorem is widely used in various fields, including economics, physics, and engineering, to prove the existence of solutions to equations and to guarantee certain conditions are met. Finally, let us apply the intermediate value theorem to example. We'll analyze functions and intervals to demonstrate how the theorem guarantees the existence of roots or solutions within a specified range. Consider the function f of x equals x squared minus 4 x plus 3 defined on the interval 1 to 3. We want to show that there exists a value c in the interval 1 to 3, such that f of c equals 0. Solution. First, let us evaluate f of 1 and f of 3. F of 1 equals 1 squared minus 4 times 1 plus 3 equals 1 minus 4 plus 3 equals 0. F of 3 equals 3 squared minus 4 times 3 plus 3 equals 9 minus 12 plus 3 equals 0. Since f of 1 equals 0 and f of 3 equals 0, and f of x is continuous on 1 to 3, by the intermediate value theorem, there exists a value c in the interval 1 to 3, such that f of c equals 0. Therefore, the intermediate value theorem guarantees the existence of a root for the function f of x on the interval 1 to 3. Through this example, we'll witness firsthand how the intermediate value theorem is a powerful tool in analyzing and understanding the behavior of continuous functions. To sum up in this module, we explored the intermediate value theorem for continuous functions. We learned about its statement, proof, applications, and saw examples, demonstrating its practical significance. Thank you for joining us in Module 9. In the next module, we will continue our exploration of continuity and continuous functions. See you there.